right? So just like in EE411, we're going to have synchronous Zoom sessions for the class. Here's the textbook for this quarter, not as thick as the 410. I'm still adding more and more stuff into this book, so eventually it's going to be as thick as the EE410 textbook. Hopefully, most of you have these copies already. It took me 2 weeks to get it. I have it with me right now. I think it came 2 weeks before, because I ordered very early. So yeah, that's the book. Just like in EE410, the book is has the same format and has the same purpose, right? Whatever you see in that book is what you will be seeing on the screen, right? So I'll be using the content of the book for my lectures. And what else? End of chapter problems, right? Those come from past midterm problems, just like in EE410. I'll be assigning homework problems based on or from this from this book. And since those end of chapter problems are from my past midterm problems, that means while you're doing your homework, you're also practicing, solving my past midterm problems, right? So that will be good to prepare you for the midterm as well as final for this class. All right. Lectures, as I said earlier, it's going to be Zoom sessions, and that's the link. That's the meeting ID with the passcode. Right? Just like in EE410, I hope that you don't mind me recording this session. I believe I'm recording these too, right? So I'm going to record all the lectures and then post it on YouTube and provide you with a link on Canvas after I upload it to YouTube. Office hours for this quarter, I have Mondays and Wednesdays. Monday is going to be from 12 to 3 p.m. Wednesdays 3 to 5 p.m. So 5 hours total. Those are the required hours. And keep in mind that the 2 office hours have different links, different Zoom links and meeting IDs. So make sure you use the right one if you are planning to join the office hours either for Monday or Wednesday. So make sure you use this link or that meeting ID numbers. Beyond these office hours, if whatever reasons these conflict with your schedule, feel free to email me if you want to set up an appointment, right, to ask questions about anything but related to this class. If you can't make it to any of these office hours, go ahead and do that. If we have in-person class, I would say that I have open door policy, right? Anytime you see my office doors open, feel free to stop by. But since we are not on campus yet, so instead of that, go ahead and email me so we can set up, a time that would work for both of us, okay, for office hours. Any question on this? All right. Grading, we have the same thing as last quarter: online quizzes, homework, final project, lab work, midterm exams, and final exams. Right. So midterm exam, there are 2 exams: midterm exam and final exam. And just like in EE410, final exam is not comprehensive. That's why it's a 2-hour exam, right? And the first exam, which is this midterm exam right there. Let's see. I was looking at the numbers, see if these are all adding up to 100%, and it seems like they are, right? 60 plus. Yeah. The first test gonna be tentatively scheduled for February 11. But final exam, that's already scheduled for March 16, okay, Tuesday for final exam. So once again, final exam is not comprehensive, just like in EE410. And then you can see that lab work is 20% instead of 25%, because I want to put the 5% into the final project as part of the hands-on, quote unquote hands-on experience for this class. We cannot use the lab yet, so try my best to replace lab experience with this final project. In the past, for this class, I assigned students. For this class, I assigned a final project where students design and build a solar-powered USB charger. So that's in the past. Every year, I assign that same project, where again students who take. I have a solar panel in the lab. So the way they demo toward the end of the quarter is that I provide them with a solar panel, and they would connect their converter into the solar panel, and the output of this converter is USB interface. And then I have my old cell phone that could be charged with USB. And so if the circuit is working, then it will be charging my cell phone, right? So that was a fun project, and everybody liked that project. But again, since we don't have that luxury this quarter, I'm going to have to replace it with another type of final project. Right? So that final project is 15% worth of the grade, and it's not as big as the hardware project because it's a simulation-based final project. Okay, we'll talk more about the final project in the lab portion of the class. So some of you will have the lab today. I'll discuss that in details later. Okay. For the rest of you, that's going to be on Thursday. Okay. Any question about this grading? So online quizzes, just like EE410, right? You have multiple choice problems, 12 minutes or so. I don't remember exactly. 10 problems, conceptual mostly. Right? Homework from end of chapter problems in the book. What else? Lab is going to be the same format as EE410. Again, I'll talk about it in the lab today and Thursday, right? Yeah, and then midterm exam and final exam. Any questions? Right. If not, homework, same thing as EE410, same thing as what we did in EE410. You have to upload your homework into a single PDF document and upload it on Canvas. You have until 5 p.m. on the due date, most likely Friday, just like in EE410, right? Homework's due Fridays by 5 p.m. I'm most likely do the same thing for 411. No late homework will be accepted. Solution will be posted on the 411 Canvas following the due date. Right? I'll talk. Oh, right there. Online quizzes will be given weekly to assess students' understanding of course materials. 10 multiple choice problems, closed book and notes, conceptual mostly, and short calculation types of problems, if any. Right? And there's limit on taking these quizzes. These are the topics that we'll cover in this class. Let me drink my water first. So we're going to start with switching losses. We'll do that today. Yeah, we'll do this today. And then snubber circuits, synchronous rectifier, and then resonant converters. This is the big topic for this quarter, resonant converters. I will provide 4 different topologies. There's numerous topologies under resonant converters. But if you can understand these 4 topologies, then the other topologies you should be able to analyze as well as understand as well, right? So that's ZVS and ZCS buck converters. ZVS stands for zero voltage switching. ZCS stands for zero current switching, buck converters. And then these 2 are non-isolated resonant converters, and the other 2 right here, these are isolated converters. So it has it's utilizing a transformer within the converter. SLR stands for series loaded resonant, and then PLR stands for parallel loaded resonant converters, right? And then I may or may not do this. If I do this, I might do it in the lab, maybe. We'll see. And then we'll do harmonics in power systems, transformer K rating, and then introduction to high voltage DC transmission, introduction to fax controllers, flexible AC transmission systems, and then three-phase switching inverters, right? So you could kind of see that half of the class deals with traditionally low power electronics, low to medium power. The other half, medium to high power electronics, right? So that way you can get exposed to applications of power electronics in different spectrum of level of power. So not just low power, but also high power. Okay. Any questions on this? All right. If not, I'll go over this in the lab, as I said earlier. This is the tentative coverage of topics for this class this quarter, right? I'll let you go through this yourself. And then more stuff on final project that I'll go over in the lab. Any questions about the syllabus?
I had a question on the lab portion.
Yeah.
You might mention it in lab, but is there any software we need to download beforehand?
No, it's going to be the same software tools that we used last quarter, LT-Spice, ORCAD, those two.
Okay.
Yeah. Anything else? No? All right. If not, let's start with switching loss for today's lecture. See if this one, yes. All right. All right, there it is. Switching losses. So this is the first topic of this class. It's a very important topic. The reason being, you probably remember from EE411, the main objective of power electronics, for power, for power electronics. What is it? You remember?
Efficiency.
Efficiency, yes. That's one very important goal of power electronics, is to be able to convert electrical energy from one form to another form in the most efficient manner, right? So in order for us to be able to process the energy without losing energy in the process, we have to come up with different ways or methods to minimize these losses, right? But before we get into how ways to minimize losses, we need to understand what type of losses are we dealing with, right? In power electronics. And the main one is switching losses, right? And this is inherent in power electronics. Again, you know this from E410, because we are dealing with switching network, right? We're dealing with switching circuits, not a linear circuit. We're using a switch or more than one switch in order to process the energy, right? So this switch is turning on and off, on and off. So in the process of changing the states from on and off or off to on, this switch will go through some losses, unfortunately, right? So by understanding why we have switching losses, hopefully then you would be able to come up with the solutions on how to overcome, how to minimize or tackle these problems with switching losses. So that's kind of the sequence of these topics, right? I'll go over switching losses first, make sure that we all understand what switching losses entail, right? And then once we understand this, then we'll talk about different ways of minimizing switching losses, right? Starting from the simplest one all the way to the most advanced one, right? The simpler way is to change components, right? That's the what do you call it? Straightforward ways to choose a different component, right? If the switch or MOSFET is lossy, then yeah, you can always buy a different MOSFET that has a better technology, or maybe more expensive MOSFET, right? Or more expensive diode, more expensive inductors, right? But sometimes you don't have that luxury, right? Of when it comes to budget. Many times our budget is limited. So what other ways can we do besides besides replacing components with more expensive ones? Well, there is, right? There are other ways. The next one will be to add a small circuit around a switch. We call it snubber, right? And if that is not a good solution for you, then there's another one. That's another way to do it, and this has to do with the way we turn the switch on and off, right? So we implement a different way of turning on and off the switch, right? And that's called soft switching. Right? So 3 different ways that I'm going to cover in this class to minimize switching losses. Okay. The first one, I'm not going to go into details because that's it's probably more of Professor Braun's area. But I can always here and there talk about how you can actually reduce switching loss by selecting certain components. Definitely from application side of converter, I can definitely cover that. But from device level, on how to improve, how to improve, what do you call it? How to reduce losses within the device itself. That's beyond my expertise, right? So I'm not going to go over that one. Snubbers, we'll go over that. There's one section on one chapter actually on snubber circuit. So we'll go over one example of snubber circuit, and then, as I said earlier, on resonance circuit, we'll go over 4 different topologies. All right. But again, before we do that, then I think it will be important for us to go over what switching losses are. Again, what do they entail, and understand how they behave, right? So that's the objective of this chapter, is for us to understand switching losses, right? Okay. So in general, there are 3 different sources of power losses in any of switching devices. The first one is static losses, and then switching losses, and then finally driving losses. Right? So static losses refer to the loss that occur when the switch, such as a MOSFET, IGBT, or diode, is fully on or fully off. So if it's if the switch is conducting, right, fully conducting current, or fully open, then there are some losses associated with those. Okay, and those losses are called static losses, again, which occur when the switch is fully conducting or fully open, right? If it's fully conducting, then we call that losses on state or conduction losses. If it's open, when the switch is open, then we call that off state or blocking losses. Okay. And then we have the second type, the second source of losses, switching losses. That's the focus of this chapter, which occur during switch transition time when it's turning on and turning off. So when the switch is in the process of, let's say, starting to turn off, let's say the switch is initially on or conducting, and then we turn off the switch. So the switch is not going to be instantaneously, turning off. It will actually take time for the switch to turn off, right? So that the fact that it takes time for the switch to turn off as well as to turn on, unfortunately, that would introduce what we call switching losses. Right? You'll see later on that the two will overlap, and when voltage and current overlap, then you'll end up with switching loss. Okay, and here's an example of that I got from a data sheet of an IGBT, right? Curves of switching losses of an IGBT. I don't know if there's a part number here. No, there's no part number, but again, I grabbed this from a data sheet of an IGBT, and you can see the three curves that shows the three curves that show the switching losses of this particular IGBT, right? You have the dashed line, then you have the dotted line, and you have the solid line, right? The dashed line, I bet you that's a turn-off loss. Usually that's the biggest. Okay, let's see. It is, right? The dashed line right there, see that? Up here, or maybe I should use my pen. Hang on. Oh, where did it go? Oh, right here. All right. So you can see that. Let me turn this laptop toward me so you can hear me. You can see from these legends right there that the dash line is for off. Right? E off means switching. Meaning turn off energy loss. And then we have the solid line that's turning on energy loss. And we have the dotted line that's for EREC. REC means rectifier, or in this case, diode. So if you put diode across these IGBTs, then this diode, actually I'm guessing this IGBT has not internal diode, but they put diode across this IGBT and put it into a single package, into a single IC solution, right? Because internally IGBT doesn't have diode, unlike MOSFET. MOSFET has internal diode, IGBT does not. So they put this diode and put the two together into one single chip solution. So with this diode that they have into this IGBT, that's the loss for that diode, rectifier, so reverse recovery. So basically recovery, not rectifier, sorry, recovery. I was wrong. So EREC is recovery. So we have the recovery loss, we have the on loss, and we have the turn off loss, right? So you can see the turn off switching loss is usually the worst, right? It takes longer time for a switch to turn off. And you've seen this in EE411, right? I don't know if you remember this. When we talked about diode, we have reverse recovery time for the diode. When it's turning off, right, it has to go through this stage that's called reverse recovery, right? And that takes time. And in fact, as I said in EE411, diodes are classified based on reverse recovery time, right? So there's standard recovery diodes, there's a fast recovery diode, there is what is the after fast? There's another one, I forgot. And then there's Schottky's, right? Schottky is the fastest, right? And then there's SBR, also the fastest, right? So so we know that diode will have turn-off losses. Same thing with IGBTs and MOSFETs. They all have turn-off losses. And again, as you can see from these three curves for IGBTs, you can see that the turn-off loss is the most compared to the other two. But nevertheless, these three represent switching loss of IGBT, right? Of an IGBT for this particular IGBT. Any question on this? No?
I had a quick question.
Yeah.
If you can hear me properly, is there any like voltage representation of this, of switching energy versus voltage? Like, why do we model it by the current?
By the current. Oh, so this is a function of collector current, right? So for IGBT, losses will be a function of, mostly will be a function of collector current. Same thing with the MOSFET too. In MOSFET's drain current. But you notice that this loss is also being measured at a certain gate to source voltage, right? So these losses will also be a function of this gate to source voltage. But the more dominant factor for these losses are collector current, the more collector current this IGBT is carrying, the more variation you have compared to varying VGS. You can see also that look at the amount of current on the x-axis. It's not small, is it? 250. This is amps. 250 amps, 500, 500 amps, all the way up to 1500 amps, right? So this is definitely a more determining factor than gate to source voltage. Okay. Does that answer your question?
Yeah, thank you.
And then later, I think related to your question as well, later we'll represent the transition when it's turning on and off, which is what we call switching trajectory, from which we can calculate or estimate switching loss. So yeah, you'll see that later, right? But in terms of data from manufacturers, typically this is what they provide. They're going to be providing you with curves of losses as a function of current instead of voltage. Okay. Any other questions? All right. So that's switching losses, right? And then the third type is driving losses. Yeah, it's not much, but when you really want to consider all losses in your converter, and this is what I usually do as well. In the past, I mentioned to you in EE411, I've done numerous consulting work for companies, and whenever I design DC to DC converters, I would in the first phase of the design, I would not include this calculation yet, right? What I did was I would include the first two losses to do what do you call it, a rough estimation of the efficiency before we even build the converter. And then once I am done with the first phase of the design, then the second phase I would include driving losses as well. Same thing goes with, for example, the magnetic loss from inductor and transformer. Usually I don't include that in the first phase of the design. I do that after I'm done with the first phase, and then I get some rough estimation about efficiency. And then if I want to get even a more accurate estimation of the efficiency, then I would start including driving losses as well as magnetic losses. Magnetic losses means that what I meant by that is these AC losses from magnetics, right? Such as skin effect, proximity effect. What else is there? Hysteresis loss, and then what's the last one? Eddy current loss, right? Those are really involved in terms of math. That's why I don't usually include those in the first phase of the design. Okay. Any question on that? So driving losses, which mainly comes from the total gate charge of MOSFETs. That's as you are turning on the MOSFET, or sorry, turning off the MOSFET, you are charging these capacitance across the MOSFET, internal capacitance. And as you are discharging this MOSFET, right? This capacitance across the MOSFET, internal capacitance across the MOSFET, you're going to end up with losses. We'll talk more about this, but the equation for that is 1/2 CB squared times F, right? As you already know, that's loss for capacitance, right? Oops, not W, sorry. That's PC, right? Power loss on the capacitor, right? So anytime you have capacitor, voltage across the capacitor, and then that capacitor is on and off, not on and off, sorry, charging, discharging, following a certain frequency, then this is the amount of loss that you'll get, right? All right.
Wait, isn't energy like conserved? Like is it like the ESR that's causing the loss?
Energy is 1/2 CV squared. That's energy, right? But if you multiply by F, that becomes power, right? So this power is power that is lost, meaning it will go through parasitic, resistance of the wires, of the capacitors itself, right? So this doesn't go to the load, this power. So you store energy, like you said, energy is conserved, but then that energy then goes away, being conserved, but the power is not being returned, or the energy is not being returned to the source, right? It's being.
Oh my God! It gets charged to ground.
Yeah, it's being. I mean, it's still reserved, right, within the system, but it doesn't return to the source, right? It's being used by the energy is being used by parasitic components. Okay? And yeah, so in the process of using this energy, you have losses, right? Basically heat coming out of resistances. Right? So that's implication of storing energy in the capacitor. Right? Capacitor itself doesn't lose energy, right? Ideal capacitor should not lose energy; it should just store energy. But unfortunately, when that energy is being being discharged or being transferred, not discharged, being transferred, it doesn't fully transfer back into the source. It goes
right. It doesn't recharge like like it's basically like injecting the current into the capacitor, and then it just kind of gets discharged into wherever.
Yes, exactly. Yeah. So unfortunately, when it's discharging, it's producing current, right? And then this current flows through some resistances, and as you know, it's R squared times R. So that's the way energy is being conserved, by dissipating it into resistances. All right. Any other questions? All right, then a little more about static losses. Let's see, with MOSFETs, we have on resistance of the MOSFET, RDS on. So if you buy a MOSFET, look at the data sheet. There is they will provide you with this data, right? RDS on of the MOSFET, and it's not a constant value. Right? Usually you'll get curves like this, as I am providing here. So on the left, you can see that RDS on the right, on the y-axis, is a function of drain current. Again, it's a function of current, right? But this is done, look, at a certain gate to source voltage again. In fact, this is a good example because you can see the difference of the two curves, right? Even though they're almost the same, but you can see that the loss is different between VGS equals to 10 volts and VGS equals to 20 volts. But the variation of the losses due to these differences in the voltage is not as pronounced as the variation with respect to the current, right? So that's why it's the more useful way to plot is by plotting it against current. So going back to, was it Nick's question earlier, all right? So that's how on resistance on the MOSFET varies with drain current. And look at the current too. This is not a small current, right? This is why it's called power electronics, because we're dealing with amps, not milliamps, right? 10 amps, 20 amps, 30 amps, 40 amps, all the way up to somewhere around 55 amp-ish. And then RDS on is also a function of temperature, junction temperature. This is something that we don't cover in this class. Steady state thermal analysis. You can see that even if you are drawing the same current, right, it doesn't mean that RDS on is going to stay at the same value, right? Let's say that your MOSFET is facilitating there you go, 30 amp of current, right? According to this curve, RDS on is supposed to be 0.5 something, right? 0.5, maybe 25. But as time goes, of course, the junction temperature of this MOSFET is going to increase, right? So when the temperature increases, so does the RDS on of that MOSFET, right? So this one is at 7.9. You see that 7.9 amps of drain current. So constant 7.9 amps, but then as temperature on the junction as the junction temperature inside the MOSFET increases, you can see RDS on in ohms also increases, right? Any question on this? So again, RDS on of the MOSFET depends on the applied gate voltage, applied gate voltage, and I should say, and drain current, and MOSFET's junction temperature. I should add that phrase here. And you'll see the same thing with IGBTs, and pretty much all the switches that we use in power electronics will follow the same type of behavior, right? That they are a function of how much current you push through it, right? As well as the applied voltage across the device. All right. This is just to show you like maybe a refresher from EE411. How do you calculate static loss? Well, you have to know current waveform, right, through the switch. And this is a typical shape of the current waveform through a MOSFET or through a switch in a buck or boost, buck boost, and so on and so forth, right? Remember this trapezoidal current waveform, right? So that happens when the switch is on, and then when the switch is off, it's 0 amp, and so on and so forth. So that's the very first step, is to be able to not recognize, but determine the current waveform, the shape of the current waveform through the switch. That's the very first step. Once you know this shape, then in order to calculate static loss, you need to find the RMS value of this current. Again, that's from EE411, right, chapter 2, and then square it, find total RMS square times RDS on for MOSFET. Right, so that gives you static loss. Right now, it looks simple, right? If you look at I switch RMS, that looks like that's not bad at all. But the equation that goes inside I switch RMS is actually this equation right here. Right? Again, this is taken from EE411 textbook. Right? For trapezoidal current, total RMS is given by this equation right here. Oh, sorry, without the RDS on. My bad. So this is RMS right here. Okay. And how do I get this equation? That's what we learned in EE411, right? You apply the RMS equations, 1 over square root of 1 over t, integral from 0 to t, remember this, right? Function of time square dt. That's one way. What is another way? Can you tell me at least 2 more ways to find RMS, total RMS?
Piecewise one, right?
Piecewise, very good. What else? One more.
Volt-second balance.
Volt-second balance? No, that's for transfer function. We learned 3 methods. We used the RMS equation that you learned in 212, right? Square root of 1 over t, 0 to t, f of t squared dt. That's the first method. Second method is piecewise linear, right? Piecewise method. If I can spell it correctly, piecewise method.
You would consider like the trapezoidal kind of thing the same thing as piecewise linear, right?
Which one?
Like finding the area of the trapezoids is kind of the same as like piecewise.
Maybe not. Piecewise is when you look at different segments, linear segments.
But it's based on trapezoids, right? Because like you have different bases, different widths, and you're kind of finding areas just in pieces, because you break it up into trapezoids.
I don't think that's piecewise. So piecewise, you just need points. You just need points. Finding areas, that's the third method. Maybe it's related to the third method. Nobody remembers? Anybody? This waveform consists of 2 components. Remember?
Oh, average AC and then the DC.
Yeah.
I don't remember exactly, but
Okay. All right. So this waveform, as you can see, the red waveform that you see here, the current waveform, is not flat, right? Neither is sinusoidal. So it's neither flat nor sinusoidal. So anytime it is not ideal DC nor it is ideal sinusoidal, that means the waveform has both AC and DC component, right? So it has both AC and DC component, right? So therefore, total RMS would be square root of the AC component square plus the DC component square. Remember that? Yes? Yes, remember this, right?
I forgot how to find the AC component though.
Oh, yeah,
I'll just read one if I'm thinking.
Don't you like normalize it or like you shift it down so it has no DC component, right?
That's correct, yes. So to find the AC component, you would take away the DC component of this waveform, right? What is the DC component? DC component, another name for DC component is average value. So the average value is this flat line right there. So if you take away the flat line, then this whole thing will shift down to something like this.
Wouldn't you still need to do the same type integral type math for the AC component?
Let's see. For this, yes. For this particular waveform, yes, I think so. But the difference is that you are breaking this down into two components, whereas this one is not, right? For this one, you get the DC component, right, which is that average value, and then you find the RMS of the what do you call it, of these AC component only component, AC component of the waveform right there.
From like a table. Like
yeah, from
so
the table.
A table would make it easier.
That's correct. Yeah, that's from the table. Well, what is this? Hang on a second. Uh-oh. Hang on. Yeah, so this is typically given in the table that I have in EE411 book. So by using the table and finding the average value, then you should be able to get the RMS of the total RMS of the waveform. With this method right here, you don't do that. You just find a function for this slope right there, right? And then you put into this equation, and that's it. That will be the end of it. So you don't really break it down into two components. Okay. Any questions on this? This is just a review from EE411. So those are the three different ways to find RMS, total RMS component of a waveform. All right. So that's how I would find this. I don't remember how I find this. Most likely from a table, from the table as well. Okay. The power converters that we study in EE411, we always assume is ideal, meaning that it does not have any losses, right? That's the first thing. And then when it turns on and off, the transition is instantaneous. So when it's turning on, it goes from, let's say, turning on a switch, then the switch current goes from 0 to whatever value, in zero seconds. Right? Same thing with the voltage. When we turn on the switch, the voltage drops from a certain value instantaneously down to 0 when you're turning on the switch. Okay. Same thing with the turn off. So that's what we assume in EE411: ideal or instantaneous turning on and off of the switch. Okay.
So like
yeah,
from last quarter, like didn't work. Could it have been because we didn't account for those in like for non-ideal behavior and our frequency was probably too fast?
Say it again.
So like if we set our frequency too fast, like the losses would have probably, I was wondering if like the losses would have like made it, like the simulation like not work. at all because like we didn't account for the time it takes to transition.
Yeah, so interestingly, even in simulation, if you use S brake or D brake, they are not ideal. So you will still have switching losses, very tiny, but switching losses. That's what limits the frequency, right? That's why you cannot keep increasing the frequency, because then you get big time, switching losses. But if the transition is ideal, then theoretically speaking, frequency is not an issue. You can use any frequency you want, right? Gigahertz stuff if you want, right? But we know that's not practical frequency, these days. But if everything's ideal, then again, theoretically speaking, you can use as high as a switching frequency you want. In EE410, when we simulate, unfortunately, those, as I said earlier, those ideal quote unquote components are still not ideal. You still have losses. For example, I don't know if you remember S brake. I always ask you to add R on resistance. Remember that, right? 10 milliohms, maybe 50 milliohms. And the reason is not because of I want you to consider non-ideality. It's more on SPICE algorithm, right? If you don't do that, then you get convergence problem. If you assign, instantaneous transition, I don't think PSPICE can handle it. Right? So you're always going to get or run into convergence problem if this is true in a simulation. Okay, so even with simulation, you want to introduce some kind of a non-ideality, right? But again, in EE410, I did that in a way that it's very tiny, right? Like 10 milliohms for RDS on of the brake, and I ask you to use D brake for diode, and that's very close to ideal. Still not 100% ideal, but it's very close to ideal. Okay, so small amount of non-linearity in the simulation component that you use in EE410. Does that answer your question?
Yeah, that makes sense.
Okay. So if we have the tool, we have the simulation to do this instantaneous turn on and off, then you should be able to implement, like I said, whatever switching frequency you want, for the converter. But when we did the analysis, though, in EE410, when we went over transfer function, when we went over what else, component sizing, right? Those when we derive those are under the assumption that we don't have any losses at all. Okay? So the transfer function that you learn for a buck, for example, that V out is equal to D times V in, that's only true if it's ideal, right? But it's good enough, right? Like I said, as a approximation, right? To approximate the duty cycle, that's good enough, right? And then the controller will take care of the rest, right? You will get a good idea of how much duty cycle you're going to end up with by applying ideal transfer function, even though you know that the actual duty cycle is not going to be exactly the same as what you calculated, right? For example, if input is 10 volts, output is 5 volts, we can easily determine that ideal duty cycle is 0.5. But we know that's not going to happen, right? We know that the actual duty cycle is going to be around 0.5. So by saying around, I think that's good enough for design, right? So that way we can introduce again what do you call it? Range of duty cycle. So instead of saying, okay, duty cycle is going to be 0.5, you can say, okay, duty cycle is going to be around maybe 0.45 to 0.55, right? So that's something that you can use when you size components, right? Worst case calculations, right? Depending on whether or not the minimum or the max gives you the worst case. Does that make sense, hopefully? Right? Okay, for example, another example is in EE410, we learned that the average current that goes through the switch is equal to duty cycle times IL, right? Remember this, right? So this is a very important equation because that's how you would size the switch, right? When you go by the MOSFET, you need to have this number, right? Let's say that number is, I don't know, 5 amps. So that's what you need to get, right? You need to get MOSFET that can handle at least 5 amps, right? But then now you know that these 5 amps may not be the worst case because that's based on ideal condition. This is ideal equation, right? So how do you correct that? Well, correct the duty cycle, right? You have to be able to determine that duty cycle ideal is going to be 0.5. Again, if it's 10 volt to 5 volt, right? But then what would be the worst case duty cycle? So it could be larger than 0.5, maybe 0.55. So if that's the case, then you put 0.55 instead of 0.5, right?
You had the ripple, right? Half the ripple.
No, for current rating, you don't need the ripple. You just need the average value. So that's why it's average value right there. Right? The bar. For voltage, yes, you need to know the ripple, but for current, you don't. You just need
Generally, can MOSFETs handle like really high spikes then?
If your MOSFET has large spikes, that means you need to fix something in your converter.
Oh, it's the inductor. Yeah,
yes,
the inductor.
Exactly.
Yeah.
Exactly. So that means your inductor is too small, right? Because then your inductor current is going to be so big of ripple like that, right? That's not good, right? So then you have to increase the inductance to make it smaller, peak-to-peak ripple on the MOSFET current. Okay, and again, we talked about it in EE411, right? The trade-off between big inductor and small inductors, right? So there's going to be a sweet spot where, obviously, if you keep increasing the inductor, then your inductor is going to be so big, right, physically, and expensive, right? But the upside is that the peak-to-peak ripple is going to be so tiny with big inductors, right? So that's a trade-off. So you gotta have to find a point, in the middle, the middle ground, the one that would be just good for your converter, right? Okay. Any other questions?
I had a quick question about before.
Yep.
The static power, why is it not dependent on frequency? Is that just the real part of the static power of the MOSFET being taken?
Yeah, it does not. It does not depend on frequency because it relates to when the current is at a constant value as well as voltage at a constant value. Right. So we take average basically of these, right? Because it happens every single period, right? So, and these both are not changing. They're all constant values. So imagine you have 10 amps at 1 volts, right? So 10 times 1, that's 10 watts, right? And this happens, every single period. So if you what do you call it? If you multiply by F and then divide it by F again, the F cancels. So you, again, you end up with the same number. But I think the answer to your question is that, it's because, these are all static. These are all constant values. They're not changing values. They're constant values, both of them. So basically DC. They're DC loss, right? How do you calculate DC loss? If you have a DC circuit, right? How do you find DC loss? You don't multiply by frequencies, right? It's just going to be V times I. Am I right? Yes.
Yeah.
Okay. So the same thing here. So think about this as a DC loss, and switching loss. You can consider that as your AC, quote unquote, even though I don't think it's AC, but it's maybe the analogy is closer to AC than DC when it comes to switching losses. Static losses is, it's purely DC loss. All right. Okay. What else? Oh, static conditions are also assumed ideal in EE410. When a switch conducts, it does not have any voltage drop. If forward drop exists, the loss from the product of current and voltage contributes to what we call conduction losses. When a switch is open, in EE410, we don't consider leakage current flowing back through the switch, right? But we do know that they exist, right? Like a diode has a leakage current, and that leakage current times voltage across the open switch should give you power loss, right? It's not big, but something that you can consider when you estimating efficiency. So that's what we assume in EE410. Another thing is that I focus on PWM in EE410, and PWM is hard switching, meaning that we are turning on the switch when the current. Imagine if the switch is being turned on, right? In PWM, what is the condition before we turn on that switch? How much current does that switch have? How much current does that switch have before we turn on that switch? 0 amp, right? So 0 amp before we turn on, and then as soon as we turn on, that same switch will carry, relatively speaking, big current. So from 0 jumps to, let's say, 10 amps, right? So that's a hard switching, right? It's like a step change from 0 amps to 10 amps. Same thing with the voltage. When we are turning it off, right? Before we turn off the switch, the voltage across the switch is practically 0, right? Because the switch is conducting. When the switch is conducting, right? Ideally, there's no voltage across it, right? And then suddenly we are turning it off, right? We tell it to open. So now a voltage appears across that same switch right away, right? Jumps from 0 to high voltage. So again, that's a jump, that's a step in the transition. That's called hard switching, right? And that's PWM, right? So here's an example. I use this LT Spice with this controller, LT1070 controller. The switch is internal to the chip. So you don't see the MOSFET because it's internal. It's a boost, isn't it? Right? You have an inductor at the front end, diode at the output, and switch in the middle. So that's a boost converter. And what I'm plotting right now is voltage across that internal switch, as well as current through that switch. Okay, so you can see the hard switching right here. You can see the red and the blue. Blue is current waveform, switch current waveform, and red is the voltage across the switch, right? So you can see easily the hard switching right here. That's turning on. No, sorry, that's turning off, and that's turning on right there. How do I know? Well, take a look at the current. Right? The easiest one is to look at the current. Blue is current, so the switch is conducting, and then all of a sudden we turn off the switch. Boom, right? So that's a step right there. At the same time, you can see voltage goes from 0 or some low voltage value goes up to high voltage, right? Okay, so that's hard switching. Same thing on the other end right there. When we are turning off the switch, turning off or turning on? This is turning off, right? And there's turning on right there. So this is on, and this is off. So when the switch is turning on, you can see that current goes from 0 to some, relatively big value. It's a jump again. And voltage the same way, from some high voltage, relatively speaking, of course, drops to some low voltage, right? In a matter of, maybe nanoseconds or microseconds, right? Very fast. Okay. So that's hard switching. Any question on this? All right, so that's what we assume, right, in EE410, that everything is PWM, hard switching. You turn off and turn on the switch, following again a PWM switching method. That doesn't have any losses in the process of turning on and off. But in real-world converters, switching does not occur instantaneously. There are rise time and fall time associated with every switching transition. This is what constitutes switching losses in power electronics. Right? So the fact that the switch does not instantaneously turning on and off, that would again create switching losses. So that's the cost. Okay, that's the cost of switching losses. Remember earlier I said we need to understand switching losses. So now we understand that the cost of switching losses is coming from rise time and fall time associated with every transition of the switch turning on and off. That's the cost of switching loss. And again, that happens because we implement hard switching or square wave switching, PWM, basically. It's a mature technology, so it's widely used, right? To these days, a lot of converters are PWM based or hard switching based. It is always then, if you use PWM, then you will always have switching losses, right? Due to due to these points right there. Right? Also due to the fact that it takes time for them to turn on and off, it would also limit switching frequency, right? Or duty cycle as well. When ideally, duty cycle could be, from 0 to 100%, right? But if it takes time for the switch to turn on and off, then you can see the duty cycle will be limited. It's not going to be 0 to 100% anymore, right? Because you have to allow the switch to go through this transition first before we can call it, on or off, right? So this takes away this transition time right there, takes away some time from the switching period, right? Which in turn limits the duty cycle. Does that make sense, hopefully? So in practice, duty cycle is not going to be 0 to 100%. It's going to be maybe 5 to 95% or something like that, right? So yeah, so if you are designing a converter and the duty cycle turn out to be 5%, I would say redesign it because that's not really practical, right? You're gonna have problem with regulation on the output voltage because it's gonna hit that low limit and you cannot even go lower than 5% when the converter is trying to regulate the output voltage, right? So you need to change the design. Same thing with the 95%. If your duty cycle, maximum duty cycle, you calculate it to be 96%, change the design because that's not going to happen. It's going to be hard to for the converter to regulate the output voltage if the max duty cycle is 96%. It doesn't have any more margin to go over 96%. Remember, you have to allow the switch to turn off, right, or on. It takes time for them to turn on and off. Okay. Any question on that? Right. And another implication would be limiting switching frequency. Right. That's another thing. Right. So imagine if these two areas right there keeps closer and closer. Right. Meaning if I keep changing, let's call it P right there. Right. If I keep squeezing the space in between this transition time, right? By doing that, and I'm moving T to the left, let's say I keep squeezing it to the left. So now the same transition time, and here's your duty cycle, basically, right? And that's the transition time right there, and there's your T right here. So you can see the new T is going to be faster frequency, right? If you compare T2 with T1, T2 will have a faster switching frequency. However, you can see that if I keep squeezing the white space in between, then eventually you're going to end up with just this, right? Just the transition time. And that's the limit, right, on your switching frequency right there. That's T3 right there. That's the minimum amount of time required, right, to allow the switch to turn on and off, right? So that, again, would limit your switching frequency, right? Now you don't have any more duty cycle if the two areas are just, what do you call it, merge into this one area right there, right? So no more duty cycle there, okay? So that corresponds to limiting the switching frequency. Any question on this?
I had a quick question.
Yeah, go ahead.
As your frequency increases, does your potential duty cycle decrease?
Yes, exactly.
Okay.
It'll be harder for you to maintain duty cycle because then you have, you know, smaller and smaller space to work with, right? Smaller and smaller time to work with. Yeah.